Okay, all right, we're going to go ahead and get started. So this is our 4 o'clock press conference, new insights into the formation of tornadoes. So today we have speaking Jana from Ohio University. Jana, take it away.
All right, thank you, Lauren. Thank you all also for staying here to the bitter end. I know this is kind of late in the show here, but so I want you all to picture in your mind, if you will, a tornado as it forms. So I'm going to give you a sec to think about that, create this little mental picture. If you are like most people, you are probably envisioning a funnel cloud that starts in the sky, in the clouds, and kind of slowly makes its way down to the ground, at which time, once it hits the ground, it becomes a tornado. So this sort of observational perspective mirrors a hypothetical description of tornado formation referred to as the top-down process. So in the 1990s, there was a study that was done to specifically look at the tornado formation process from radar data that was taken from large radars that are from a national network. And basically, in this study, about 67% of the tornadoes that they observed formed in this manner. However, there are also some additional hypotheses that exist that specify different ways and different mechanisms of these theories. So one of the important things to note here is that there is actually a little bit of a timing discrepancy and a timing issue here. So if you take a look at these images on the left-hand side, we have a picture of a low-hanging wall cloud, and then we see a funnel cloud form, and then we see this very large tornado on the ground. Well, one thing to note is you can probably not see very well, but the times here, there is 4 minutes and 10 seconds between this image here and this image down here. And in fact, this image and this image were actually taken essentially at the same second and just several hundredths of a second apart. So the top-down process notoriously is going to describe the tornado formation process occurring on the order of about 5 to 10 minutes. We have an observational data set that argues that this might not necessarily be the case. So this begs the question, do tornadoes really form from the top down, or is there perhaps something else actually at play here? So to get right to the point here, in 4 out of 4 of the detailed data sets that were analyzed for this study, none of the tornadoes formed in this mechanism, and they've all formed from what is referred to as a non-descending pattern. So the graph that you see here shows a chronology of the evolution of the signature that is evident in radars that is associated with tornadoes in time and in height. So this is for one of the 4 case studies that was specifically dealt with for this study. And we can see very clearly that rotation existed first at very low levels, and then basically within about 30 to 60 seconds, we go from having rotation at the very lowest levels only to a depth of about 3.5 kilometers, which is basically where the data acquisition terminated. So the results are basically that in these cases, the radar detected either a sudden spin up to tornadic strength kind of simultaneously over the depth of the column that the tornado was observed, or a rapid buildup from the bottom. And also it's important to note here that this process occurred from on the order of about 30 to 90 seconds in at least 3 of the 4 cases. The 4th case, there was some rotation that already existed prior, so that was a little less clear. And one really important data case that was a really strong asset to this study was the 31 May 2013 El Reno tornado, which was a violent tornado noted in historical context, actually, for its size, its strength, and some other reasons as well. But with this particular database, we had a really strong visual acquisition of data that was put together from storm chasers. And basically, we had this unprecedented database that brought together all of their videography and their photography and was able to really look at this storm and the evolution of the storm in a way that has never really been done before. This was coupled with high-resolution, rapid scanning radar data that was acquired at elevations of less than 30 meters. We could, perhaps argue perhaps even as low as 15 meters or so above the ground. So the data that went into this study, there were 4 specific events. There was also a 5th event that we touched upon that wasn't quite ready for showing here. But out of those 4 cases, 2 violent tornadoes, 2 weak tornadoes, none of them, again, established that top-down evolution mechanism there. We used the rapid scanning X-band polarimetric mobile radar from the University of Oklahoma, also known as RAXPOL. This radar is really particularly special because it collects data very quickly. You can get a sample of the atmosphere in 30 seconds compared to what it would take the National Radar Network on the order of about 5 minutes to collect data with the same sort of spatial coverage. And then we also coupled this with the visual observations, as I alluded to, from the Tornado Environment Display tool that was put together by Anton Simon with the El Reno project. But that was only for that, that's actually the wrong date there, it's 31 May 2013. And that had basically these unprecedented crowdsourced video and photography data. So what I did is I tracked the radar signature associated with a tornado. You can see this over here. The radar would be over here. And basically, you have strong rotation or strong motion away from the radar here, strong motion toward the radar here, and you can imply that that means there's strong rotation there. So this is our tornado. And I tracked this signature with time and with height for roughly 5 minutes prior to the time that tornado genesis was specified to occur, or the tornado formation had occurred, and then several minutes after the fact as well. And then I coupled these radar observations with the visual observations from the 31 May 2013 case. This is a screenshot of what that tornado environment display software tool looks like. It's a web-based tool, and you can have different viewing angles of the tornado. So one thing to note here is that, actually, can I go back a slide or two? Yeah, so let me go to this one, actually. So one thing that was really important that we noted when we basically took the radar data and coupled it with the visual observations was that we had a visual of a tornado funnel on the ground at a time when there was no evidence in the radar data that this tornado actually existed, except at the very lowest elevation angle, which was again at a height of about 20 to 30 meters or so above the ground. So the next data point available was at about 250 meters or so. So this tornado, in this case at least, was very much confined to the lowest layer of the atmosphere, and it could be argued was almost a surface-based type feature here. And that was really justified that we had a tornado there by the use of this visual database. So in conclusion, some kind of last-minute takeaways, musings, is that what we're learning from these data is that tornado formation is really a very rapid process. So we're talking about, processes that are occurring on the order of 30 to maybe 90 seconds. So unfortunately, from a forecasting perspective, this is not particularly encouraging. So we perhaps might need to argue that we have to have a little bit of a change in philosophy with how we're issuing tornado warnings based upon the physical processes that we're uncovering here. Also, I didn't particularly touch upon it here, but these results also seem to suggest that there might be some small-scale and even local processes that are important in the formation of tornadoes that could be potentially, independent or dependent of location and a case-by-case basis that would basically imply that it's going to be hard to establish a sort of more generalizable type of concept to all tornadoes, so it's not particularly ubiquitous. And then also it's important to note that our eyes also likely deceive us with this top-down idea. So we are able to discern from the radar data that we have tornado strength rotation on the ground sometimes when we don't even actually have visual observation of that tornado. Now that might be because there's a little grove of trees on the horizon, or there's not a whole lot of debris that's available on the ground to be lifted by the tornado. But the idea is that our eyes are probably not giving us really the full picture here. And then lastly, the biggest takeaway point here is that based on these cases, as well as a few others that have also been completed, tornadoes do not appear to form from the traditional top-down mechanism as sort of had been prior or previously established. So with that, I will end my little blip and take questions.
Of course. Seth, you can always go first. Just remember to state your name and affiliation.
Seth Bornstein, AP. I was talking to Paul Markowski about your paper, and he said one of the things that struck him sort of as a straw man argument was that we think tornadoes are top down. He says ever since the 80s and Bob Davies Jones, we've known that you have the air going up, that you need the air going straight up for a tornado to form. So I mean, is it don't scientists already know that tornadoes, that you've got that the air rushing up first to form the tornado? So I'm just wondering, is this premise that you're disproving not really there anyways?
Right, that's a good question, and I think it would sort of depend on who you ask in the community about that. There is still a pretty pervasive sentiment that tornadoes form from the top down. I would say that over probably the last 5, maybe even 10 years, this has started to perhaps change a little bit, but the key element here is that observationally we have not had the ability in a time resolution sense to confirm this for sure. So while we've sort of had these theories that have been posed and different arguments being made for one side or the other side, really the observations have been lacking to definitely confirm this. And even, getting down to extremely low levels where we're really looking at rotation within, the lowest 100 meters or so of the atmosphere, that's relatively new.
And I did forget to mention, actually, Anton Simon, who's another co-author of the paper, is also here to answer questions, too, if anyone has questions for him.
Hi, Carolyn Gramling from Science News. You mentioned that we would potentially need to have a change in how we issue warnings based on these physical processes. I was wondering if you could elaborate a little on that. How is it done now, and how would you suggest it?
Sure. Yeah, so I have been in contact with the National Weather Service, and I've actually done a couple of webinars with some of their forecast offices in the Central Plains, and we've had some discussion about this. There's kind of currently this, not to oversimplify things, but yes to oversimplify things, meteorologists who are working in an operational framework tend to look at the structure of a storm, and they tend to consider the environment that that storm is forming in, and they look for key specific features that that storm might possess that would be an indication that it could potentially become a tornado-producing storm. So even just kind of with that framework, you can see that it might not necessarily, if we had truly a top-down process where you are seeing strong rotation evident in the middle levels of the storm building down, hypothetically, that would be somewhat encouraging for forecasters because they could look for this in the radar data that they're observing. Now, as we're kind of more and more disproving this, you can imagine that having 100% confidence based on observations and issuing a tornado warning on those observations is pretty much not ever going to happen. So one of the more perhaps promising alternative routes that's being looked at by people at like the National Severe Storms Lab and perhaps some other places as well, is to take a forecast, take model data, and basically look at that model data, high-resolution model data that are being forecast out just several hours in advance, and look at which storms, we're actually resolving individual storms in this situation, and perhaps arguably sometime in the near future, if not even now, I'm not 100% sure what the current status is, but looking at these storms, and perhaps they're even able to resolve features that resemble tornadoes in these models. And then basically take these forecast models and look for similarities in the real environment and see where storms are forming in the real environment. And if you have a storm that is in the model looking like it's going to be a tornado-producing storm, if you see something similar in reality, then you can be more confident in issuing a tornado warning based upon that model output. So that's perhaps one avenue that is being pursued and could potentially offer a little bit more promise to this forecasting and warning problem.
Do we have other questions from reporters in the room? We have a question on the chat.
The first question is from Catherine Cornide, freelance. Where were the 4 tornadoes located?
So these 4 tornadoes were all Central Plains tornadoes. They were all formed by supercells, which are large rotating storms that are responsible for producing the largest, most violent tornadoes. So 2 of these storms were from central Oklahoma, and 2 of these storms were from kind of southwestern Kansas area.
And the second question is from Angela Fritz at the Washington Post. Isn't it possible, even within your results, that tornadoes form top down and that the first thing the radar sees is the debris on the ground? It's not going to pick up strong reflectivity or velocity from the funnel until it has debris.
So we can see there is enough meteorological scatterers within the region where the tornado is or would be forming, at least a little bit above the ground, that we definitely have the ability to see that rotation within the context of the cloud-bearing layer. So yes, while it's true there might be a little bit of a gap there between the base of the cloud and the location of debris on the ground, that spatial layer is relatively small and we can still see the rotation above that. So if the descending tornado process was actually happening, we do actually have good coverage of the rotation in those sort of middle layers of the storm.
Seth Bornstein at AP again. Can you actually go through these 4 cases that you have, and tell us not just generally where, a little more specifically where they were, what their EF was, and given that, you have 2 weak and 2 violent. Once you give us the EFs, it'll be a little bit better. But is there a sense that this is the situation with only certain size, or or can you make this all tornadoes? So how can you and do you have enough with just the sample size of 4 to generalize?
Right. I think the sample size is the bigger issue here, not so much the intensity of the tornado. But to give you the information you asked for, the 24 May 2011 tornado was a violent tornado that occurred outside of El Reno, Oklahoma, that was rated an EF5. The 2012, both of these tornadoes, one was Galatia, Kansas, the other was Russell, Kansas. One was an an EF1. Actually, they both were EF1s here. So they were relatively weak. And then the 31 May 2013 tornado was, again, outside of El Reno, Oklahoma, in an area that was slightly to the east of the 2011 tornado. That was rated an EF3 on the EF scale. However, I will say that EF ratings are based on, again, damage indicators and not so much the actual wind speeds of the tornado. So the radar observed wind speeds don't necessarily exactly agree with the EF ratings.
I thought that was a little more violent than the 3.
It was rated an EF3. Yep, even though the wind speeds were in the 300 miles per hour range. Okay, and then what else did you ask? I'm sorry.
Just in general, would this be large?
Oh yeah, so unfortunately with tornado observations, we suffer from the perpetual problem of availability of the data and getting our equipment to the right place at the right time, and it is logistically very challenging to get good data sets. Plus, we don't know beforehand when these storms are going to produce tornadoes. So many hours of data are collected on storms that never end up producing tornadoes. So being, again, in the right place at the right time is challenging. So with that said, we have relatively few high-quality case studies of tornado formation. So these 4 are 4 of the ones that are available in the database with this particular radar. There are at least 2 others that haven't been investigated quite as thoroughly. So yes, sample size might be potentially an issue. However, I want to actually elaborate on something that I mentioned earlier at the very beginning of this talk, with that study that was done in the 1990s that found roughly 67% of tornadoes formed from the top down. So that was using, again, this national radar network, and these radars are located relatively far away, and they have temporal resolutions. Roughly, you're scanning the same part of the atmosphere once every 5 minutes. So what I'm hoping to argue here, and hopefully that you're seeing this, is that once every 5 minutes is not nearly adequate for sampling these storms. So, but based upon that 67% statistic that they found, hypothetically, you would expect at least 2 of these 4 tornadoes to form, and their sample, by the way, came from, at least in the supercells that they studied, came from the Central Plains. So we're talking geographically similar areas here. So you would hypothetically expect at least 2 of those 4 to be producing tornadoes from an alternate method, and we did not see that.
Harvey Lyford, freelance. Excuse me. In that earlier study, when 2/3 were found to be top down, what were the other third, undetermined or ground
Yeah,
up or
they specified as just descending or non-descending, so basically some other mechanism. And basically, they looked at storms that were not just supercells, they also looked at squall lines, which are more linear, and they're known to have different formation mechanisms for tornadoes, and they found that the majority of the non-descending ones that they found were associated with squall lines. But really the issue with that study was the temporal resolution, and that I have a colleague who mimicked the time resolution that the 88Ds have, which is that national network, using rapid scan data, and basically he, using the same criteria that other study had, was able to define storms that in the rapid scan data set actually formed in a non-descending way, but using the degraded temporal resolution, they met the criteria for the top-down process, actually. And part of what was responsible for that was basically you have these transient little short-lived spin-ups that look like they might be a tornado forming, that are there for 10, 20, 30 seconds and then go away. And basically that was what he attributed to this sort of false signal of the top-down process.
Do we have other questions from reporters in the room? Oh.
Just one more, Harvey Lyford again. The radars that detected the 4 in your study, were they on that mobile unit or were they normal Weather Service radars?
No, they were all based on this radar that you see right here. This is a rapid scanning mobile platform here. It operates at 3 centimeters and again scans very rapidly.
Do we have any more questions on the chat? Yeah.
Catherine Cornai, freelance. What's the challenge to getting radar that traces the ground area, which seems necessary?
Yeah, that's a really good and important question. The issue is that a radar beam is not like a laser. Okay, it's not perfectly kind of aligned and straight. It actually has a beam form that's more like an ice cream cone. So as you are scanning out, you're actually intersecting other objects that are on the surface, like trees and phone poles, et cetera. So in most cases, when you're operating with one of these radars, especially if a tornado is, even as few as 5 to 10 kilometers away from your deployment location, you actually have to tilt the antenna up in order to make the beam go over these contaminating type of objects that are on the ground. What made the El Reno 2013 data set so extraordinary from a radar perspective is that we were deployed on a slight elevation, on a slight hill, that enabled us to basically collect data perfectly straight out from the radar, which ended up being just a little bit above the ground, and it was just enough, the tornado was close enough to us that we didn't have to worry as much about all of this contamination.
Do we have any more questions? Yeah, in the room?
Helen Santora, UC Santa Cruz. I'm wondering if moving forward you'd be interested in using this same radar system in other parts of Tornado Alley to see if your results remain consistent.
We have done that. We just have not had quite as much success in actually collecting the tornado formation process. But yeah, we're not necessarily geographically confined to, Oklahoma and Kansas. I will say, however, though, that operating in places further to the east, like once you get into, even parts of Missouri or Alabama or the southeastern United States, it becomes unfeasible to operate a radar in those locations because there is too much in the way. There's too many trees, too many hills. There are not locations that are favorable for sticking a radar and having a good clear view to the storm. Also, storms tend to move a little bit more rapidly in that part of the country, which makes mobile deployments a big challenge.
Do we have other questions from reporters in the room? Do we have any other questions on the chat? Okay, well, that will conclude. And thank you, everyone. And that is literally a wrap. No more press conferences for the rest of the meeting. Thank you all so much for coming.
Thank you.
Thank you, Jana.